So this is a little video on checking the assumption of equality of variances. So if our data don't meet the assumption, we have to do different tests, as you already know. And this one is just looking to see if the variance across these two groups is equal enough. You can see here that I'm using the same example from before. I've got the prayer ceremony condition versus the late night study session with a measurement of test anxiety using simulated data. And you can see that I've gone a step further. I've done initial calculations. I found the n degrees of freedom, the mean, the sum of squares, which I got by subtracting the mean from each score and squaring it, then summing them up here, and finally dividing by degrees of freedom to get EVAR. And you can see the formula here. That's what we've done. And we've done it on both sides. That'll give us a supporting point for analyzing the variances. Now, the first thing that is a good idea to do always, you do it for checking normality as well as just glancing at your data for variances, is to look at your data. And inserting a nice histogram can be really helpful that way. So I'm going to just insert a histogram of these data right here. I'll go to insert. I'll click on the histogram here and insert that histogram. And to make it meaningful, I need to click down here on the x-axis and then right-click, come to format axis. And once again, you may come up on this. You may come up on this. What we want is this. We want to somehow get more bins on there. I'm going to actually select the number of bins. I'm going to say 10 bins and click OK. And so now we have a histogram. We can take a look at what our data are showing. I'm just shrinking it down a little bit to put it side by side. One of the first things I can look at are the two ranges. And I can see, looking at the scores on the bottom, I can see that this first data set ranges from 21 to 32. This histogram is ranging from 21 to 34. So right here, we can see that the range and the spread, which is what we're really looking for, is fairly close. So that looks promising for our data. The next thing we do is we check our rule of thumb. We're going to divide larger variance by the smaller variance and look for a score of less than 4. So I can look up here at our variances and see in just by glancing that we have a 17 here, or rounded off to 18. Divided by 11, I know that's not going to equal 4, so we're looking in good shape there too. I'll run the statistic equals, let me click in the cell, divided by 11, larger by the smaller. I get a 1.6. Since it is less than 4, let's put an interpretation in here. Since this quotient is less than 4, it suggests normality. But we know that this test is susceptible to the number in the sample, so we are going to go on and do Levene's test for equality of variances. And just to orient you a little bit to this test, I wanted to parse the problem like we have done. And I'll write this in for us because it'll be helpful. In this kind of case, what we're actually doing is a statistical test. It's an F test instead of a T test, but we can still conceptualize it in a similar way. So let's say our population 1 is going to be individuals like those in our sample compared with, I should say, individuals like those in sample 1 compared with individuals like those in sample 2. And let's and what are we measuring? What we're measuring is something we call absolute deviations. And all that means is this deviation column here, if we took away the sign, we'd have an absolute deviation. And then if we used this column without the signs and this column without the signs for our statistical test, that's what we're doing in this Levene's test, but we're actually calculating a ratio as well. So it's a little bit different, but that's what we're comparing. Absolute deviations, that is the deviations that we calculated for each score without the sign. If our data were skewed, instead of subtracting the mean, we'd subtract the median. We don't have skewed data, so we're going to leave it at the mean. We already checked these data. The F test is always a one-tailed high test because it's comparing ratios which cannot be less than 0, and the bigger the ratio, the greater the difference. Our research hypothesis is just that population 1 will have different variances, absolute variances. Let's say absolute deviations from population 2. And for our null hypothesis, population 1 will not have different absolute deviations than population 2. We're looking at this F distribution, meaning that we're going to go to ratio. So just as we did this statistic, if you can imagine this statistic plotted here, we can see that a 1.6 would be right around here. It would fall in the fail to reject region. This is the reject region. But we can't rely on that 1.6 because of the problems with sample size. So that's why we actually run the full S test using those deviations. This rule of thumb gives us a hint, though, that we're going to be okay. And so let's run this Levene's test and plug the result in. So the Levene's test is right here. So in our case, we're going to just enter our data and put them in. Just a couple parameters you can establish. We can leave alpha set to the way it is. Let's use the mean because we don't have a skewed distribution, so change that to mean. We'll leave effect size to medium. We're not taking out any outliers. We're doing an F test. We can leave this stated 0.25. You'll notice it's different than the effect size standards or norms or conventions that we had for the t-test. Just leave that alone. That's because it's an F test. So let's go ahead. The first thing we want to do is get rid of group 3. We have only 2 groups. So click in that group 3 column, scroll down a little bit and hit delete column. Next, we can copy and paste our data in here. I'm going to get it right from the spreadsheet. I'm going to copy down our test data. Don't copy in those deviations, just get the test data. So let's paste this in here. And let's get the other sample and paste it in here. And now we can go ahead and calculate. And we did get the result. It said our validation, we had success. And the result that we got is right here. I'm going to copy it in so that I can interpret it. And then I'll show you there's some value in this tool. Like every single number here you can hover over if you don't understand what the number is, and it will help you. And there's even a good explanation down below. For now, I'm just going to use my snipping tool and grab this and paste it into our spreadsheet and interpret it. So going down here, it was looking promising in the first place. Now we paste this in. Let's interpret that result. So it looks like, first off, our F statistic, F equals 0.3849, which is nice and low. Now remember, what we want in our test is we want to fail to reject the null. We want the null to stand because we don't want different deviations. And so what we have to do is look at our F test and then see if it's significant. And we already know that a p-value of 0.5443 is greater than p less than 0.05. So in other words, this tail of the distribution, our sample score, the 0.3849, is like way over here. It's right in this very normal, in this fail to reject region. And so we can be very comfortable. We can make the decision that we're going to fail to reject the null, so the null will stand. We know that we don't have different variances. We can say that then here because P is greater than 0.05. We don't reject HO, and HO stands. The 2 samples do not have significantly different variances. We can use the normal student t-test to analyze our data. So we met the assumptions of normality and we met the assumptions of equality of variances. Now, in some cases, though, we might have unequal variances, and let's look at what that might look like. So here I've just changed the data to make it a little bit different. I can create the histogram for the second sample and we can observe some things. So here's our histogram. Did I get the right data? I think I forgot to put the data in. Let's select the data and try that again. Insert histogram. And now we'll just do that same thing where we change the axis. Let's format it and set it once again to 10 bins. Enter. And so now we can sort of compare these two and look at some of just eyeball our data and see what it looks like. And if we just eyeball these two charts, one thing we can observe is that the range is quite a bit bigger on this new sample. Here we have that range of 21 to 32, but here this is ranging from 21 to 42. And so this is quite a bit bigger. Even though we can't see it on an equal continuum, we can see that this one is quite a bit smaller. All right. So let's check the rule of thumb. As indicated, I already calculated the variances, and here we have 53 compared to 11. That looks like it's going to be greater than 4. So let's go ahead and check it. Equals, I'll choose the larger of the two, which is this 53, and divide by the smaller, which is this 11. And I get 4.81. It's larger than 4. The quotient is larger than 4, suggesting inequality of variances. But we have to double check because that, again, is contingent on sample size. So let's go ahead and run the Levene's test. I have these, I'm going to just copy in these data and paste them into place. So here is our Levene's test calculator. Let's paste in these new data for group 2 and see what happens here. So first off, let's calculate. First off, we can see that there is a test of normality. We could probably dig in and find out if this is the Shapiro-Wilk, but either way, results closer to 1 are more normal. We could see that we're a little bit hinging on some skew. It doesn't appear to be great enough to be a problem for normality. So that's why we can stay with the mean up here. But we should just be cognizant of that for that second data set in case we get weird results. So what is the actual ratio? We have an F statistic of 4.6677 and a p-value of 0.04732. Let's copy this out. This looks problematic because our p-value, well, it's red for one thing, they're giving us a nice warning. And they're also indicating here that these are not considered to be equal. So the dogs, let's paste it in here. And here we can see that since the p-value is less than 0.05, we reject the null hypothesis. That means that our sample score 4.677, is falling way out here somewhere. It's in this reject region. We reject the null. Let's reject it. And we conclude that population 1 has different variance than population 2. So that's our conclusion. Our sample does not meet the assumption of equality of variances. We will need to do the Welsh test, the Welsh t-test for these data. And I'll give another demo of exactly how to do that.